Welcome to AI Paper Slop. Today we are looking at a brand new paper called Self-Gradient Forcing Native Long Video Extrapolation by Junhao Wang and researchers from Joy Future Academy, JB.
Yeah, and we are going to just get right into the core insight for the ML engineers tuning in. The big breakthrough here is that autoregressive video diffusion models, which are normally trained on just a tiny, 5-second window,
Right.
can now generate highly stable minutes-long video. We're talking up to 240 seconds without any view jumps or identity drift.
Which is wild. Going from 5 seconds to 4 minutes is a massive leap.
Yeah.
How exactly are they pulling that off?
So they solved this issue called the historical context gradient gap. They use a two-pass training strategy, which they call self-gradient forcing, or SGF.
Okay, SGF. Got it.
Yeah, so pass one does a completely no gradient rollout, and then pass two basically reconstructs the exit step in parallel.
Oh, wow. So they reconstruct it so they can apply the loss.
Exactly. It allows future distribution matching distillation losses, or DMD losses, to train the model on how to actually write into the KV cache.
Yeah.
And they do it without causing an out-of-memory error.
Right, the dreaded OM error. So the mission for today's deep dive is to figure out why frozen KV caches totally fail in long rollouts, right? Like, we need to understand the memory constraints of backpropagation through time and diffusion and how this new algorithm cleverly sidesteps all of it.
Yeah, to really appreciate the genius of SGF, we kind of have to look at the bug it's fixing in current video diffusion training.
Yeah, let's talk about the baseline. Why does long video generation fall apart after 60 seconds right now? I mean, what is the industry standard that this is replacing?
Well, historically, the baseline was teacher forcing.
Right, TF.
Yeah, TF. And with teacher forcing, you condition your models on ground truth video context. So during training, you are feeding the model perfect real-world pass frames to predict the next one.
Makes sense. It learns fast because it has a perfect foundation.
Exactly. But the problem happens during inference. When you actually run the model, it doesn't have those perfect past frames anymore. It has to condition on its own self-generated history.
Right, which is going to be a little messy.
Yeah, and that mismatch between the perfect training data and the messy inference data creates what we call exposure bias.
Exposure bias. You know, I always think of exposure bias like learning to ride a bike with training wheels.
Oh, that's a good analogy.
Right, because teacher forcing is the training wheels. You feel totally balanced because the ground truth data is physically holding you up. You're pedaling fast, feeling great. But then during inference, someone suddenly takes the training wheels off.
And you just crash.
Exactly. The model wobbles, the scene collapses, because it's never actually had to balance on its own shaky self-generated history before.
Yeah, that maps perfectly. So to fix the training wheels problem, researchers moved to a technique called self-forcing, or SF.
Okay, so how does self-forcing handle the wobble?
It mitigates exposure bias by forcing the student model to train on its own autoregressive rollout. So instead of perfect frames, it generates a sequence, and you supervise that self-generated sequence using DMD, which you mentioned earlier.
Right, distribution matching distillation, meaning we use a powerful bidirectional teacher model to give a score to the student's messy video.
Exactly. The teacher says, here is what a real video distribution should look like, and provides a loss signal.
But wait, this brings up a huge contradiction. If self-forcing fixes the training wheels issue by letting the model generate its own history and the teacher corrects the wobble,
Right.
why does it still fail? Like, why does the video of a boy eating a burger still morph into an old man drinking coffee after 60 seconds?
Yeah, that is the exact bug this paper uncovers. It is the historical context gradient gap. In standard self-forcing, the historical KV cache is completely detached.
Detached, meaning what exactly?
It means it's treated as a frozen rollout state. So think about the read versus write dilemma here. Future DMD losses at those noisy time steps can train the denoising computation on how to read the cached history.
Okay, so it gets really good at looking at its pass frames.
Right. But because the cache is detached, the losses cannot backpropagate into the clean time step computation, meaning they can't reach the exact time step 0 or $t that actually wrote those historical KV entries in the first place.
Oh, I see. So it knows how to read the memory, but it's never taught how to properly write it.
Exactly.
It's kind of like, okay, imagine you're writing technical documentation in a massive rush, right? Later on, your code fails because the docs are unreadable.
Right.
That failure is your loss signal. So you learn how to squint and read your own bad handwriting better.
Right. You adapt to the bad notes.
Yeah, but nobody ever goes back and teaches you how to just write clearly in the first place. The loss never reaches the writing process.
That is exactly what happens. And because the diffusion transformer, the DIT, shares parameters, the unsupervised writing path gets corrupted over time.
Wait, the shared parameters drift.
Yeah. The parameters get updated to read bad handwriting, but since they are shared, it unintentionally corrupts how the model writes to the clean time step cache.
Oh, wow. So it's actively getting worse at writing its own memory? That's a huge bug.
It is.
But then I have an obvious software engineering question here. If the problem is just a detached cache, why not just turn the gradients on? Like, just set requires vigorous grad to true on the historical KV cache.
I mean, that's what everyone asks at first.
Right, because we have 80 gigabyte H100s now. Can't we just brute force the memory and let PyTorch do its thing?
You literally cannot. The math of OMAD of memory makes it impossible for long rollouts. The paper's appendix actually details 3 scenarios to prove this.
Okay, lay them on me.
First is the baseline, frozen cache self-forcing. That takes about 79 gigabytes.
Wow, so it barely fits on an H100 as it is.
Exactly. Now, scenario 2 is your idea, the direct differentiable cache. If you do that, you retain the serial cache formation graph.
Meaning I have to save all the activations.
Yes. You're saving activations attached to the recurrent cache trajectory. And because it's a serial loop, the memory blows up immediately. Immediate ohm.
Ah, okay. Think of backprop like trying to undo a massive, complex knot in a string. The string itself, the K and V tensors, doesn't take up much space.
Right. The final state is small.
But to calculate the gradient, you have to keep a high-res photograph of every single time your fingers twisted the string for every layer across the whole timeline.
That is a brilliant way to picture it. You're not storing the string, you're storing millions of photographs.
And the VRAM just goes up in smoke? What's the third scenario?
Full rollout BPTT. Back propagation through time. Here you retain not just the cache formation, but the entire denoising trajectory.
Oh, forget it. Massive memory blow up.
Yeah, it's not even close to fitting on a GPU, so brute force is entirely off the table.
Okay, so we're stuck. We need the gradient to fix the writing problem, but tracking the gradient melts the cluster. How does SGF, this algorithm 1, cleverly sidestep this?
This is the 2-pass bounded reconstruction we mentioned. So pass 1 is the no gradient self-rollout. The model does a completely normal serial autoregressive rollout.
Like it would during inference.
Exactly. No gradients. But it records the self-generated context and the noisy latents at a randomly sampled denoising exit step.
Okay, so it just flags one specific exit step and saves it. What happens in pass 2?
In pass 2, the rollout cache is entirely thrown away.
Wait, dumped from memory.
Completely dumped. Instead, that recorded exit step computation is reconstructed in parallel. The generated context acts as a stock gradient input, but the model recomputes the clean context KV representation.
And the causal attention, right?
Yes, the future to context causal attention is recomputed.
That is so elegant. So we are basically turning a serial infinite graph retention problem into a bounded parallel recomputation problem.
That is exactly what they did.
We only open the gradient tape for the exact slice of time we need to supervise the KV writer. We avoid the recurrent autograd graph entirely.
Yep. And because you bound it, the peak memory is only about 87 gigabytes.
Oh, wait, really? Only 87. That's barely more than the frozen self-forcing, which was 79.
Exactly. But you get massively better training signals because you finally close that context gradient gap.
Okay, so the training bug is squashed. But what about inference? Because if I'm a user and I want a 4-minute video, how does the model actually manage that context window during streaming? It can't hold 4 minutes of high-res video in the cache.
No, it can't. Both SF and SGF use a sync plus FIFO context policy for streaming.
Okay, FIFO is first in, first out, like a sliding window. As new frames generate, old ones drop off the back. But what's the sync part?
The sync latents are the very first few tokens of the video, and they get permanently locked in memory. They never drop out.
Like an anchor.
Yeah, but the paper ran a really specific VAE diagnostic on this. A causal video VAE compresses frames into latents, right? And they found that early latent frames actually act as a transition boundary, not just an isolated token.
So how many sync tokens do you actually need to anchor the scene? Like, is 1 enough?
If you use a sync size of 1, you lose boundary information, the aesthetic quality drops, and you get really bad flickering.
Oh, because it doesn't have a firm grasp on the initial state of the video.
Exactly. But they found the sweet spot is a sync size of 4.
Why 4?
Because it perfectly preserved the boundary transition prefix induced by the WAN video VAE's asymmetric grouping pattern.
Ah, okay. The VAE groups them asymmetrically, so 4 tokens perfectly captures that initial boundary state. Lock those 4 in, and no more flickering.
Precisely.
All right, so we've got the theory, the memory profiling, the inference architecture. But let's talk about the actual output. Does this give us better AI paper slop?
Oh, it absolutely does. Keep in mind, these models are trained on a tiny 5-second window, but evaluated on 60-second and 240-second extrapolations.
All right, using movie gen prompts and vbench long metrics. What did the visual evidence look like?
Remember the burger boy example?
Yeah, the boy eating a burger in a diner.
Under teacher forcing initialization, the baseline SF model stays plausible for a bit, but it slowly drifts into view jumps, scene breaks, and total identity drift.
By minute 3, he's an old man.
Exactly. But with SGF, it keeps the boy, his pose, and the restaurant layout totally consistent for the full 4 minutes.
Wow. And what about the sea turtle prompt? They used causal CD in it for that one, right?
Yeah.
Conditioned diffusion.
Yeah. For the turtle and the elephant prompts, the SF baseline suffers from this really bad crop drift.
Crop drift, like it just zooms in.
Yeah, it systematically zooms in until the scene context is completely lost and the object is clipped out of the frame.
Just like the virtual camera forgets how to stay still.
But SGF locks in the camera distance and scale perfectly.
That's incredible. Now, there is one metric anomaly I want to bring up for the ML engineers because it's super fascinating. SGF actually scores lower on the dynamic degree metric than SF in some cases.
It does, which sounds counterintuitive.
Right. You'd think a higher dynamic degree is always better, like more motion equals better video. But you were saying earlier that the SF models are scoring high for a really bad reason.
Yes. The camera geometry is breaking, the objects are deforming. It looks to the algorithm like there's a lot of motion, but it's actually just glitching out.
Right. The system is just hallucinating chaos, and the automated metric rewards it. SGF is stable, so it ironically gets penalized on a raw motion metric.
Which is exactly why they ran a massive human preference study. They did a GSB good, same bad blind user study with over 1,900 paired judgments.
Now, I'm guessing the humans didn't prefer the glitchy mess.
Definitely not. There was a definitive human preference for SGF across both frame-wise and chunk-wise generation.
So to quickly summarize all of this, solving the historical context gradient gap basically allows native autoregressive models to stop forgetting their own visual rules during long generation.
Yes, by doing the two-pass reconstruction, we bound the memory while still delivering that crucial gradient to the KV writer.
Which honestly leaves me with a really provocative thought for you to mull over. SGF proves that how an AI writes to its own memory is just as critical as how it reads it.
Oh, for sure.
So if we can bound the memory costs of context gradient reconstruction for video diffusion, what happens if we apply this exact two-pass strategy to autoregressive LLMs?
Oh, that's an interesting idea.
Right. Because text models are dealing with massive, infinite context KV caches right now. Could this solve the lost in the middle phenomenon for text models without blowing up our GPU clusters?
I mean, the math should theoretically carry over. It could be huge for LLMs.
It's definitely something to think about. Thank you so much for tuning in to AI Paper Slop. Keep building, keep reading, and we'll catch you on the next deep dive.